Ladies and gentlemen, in this talk we'll learn something about forces between molecules, force fields, and lattice models. Let us say, two atoms of argon, one of the simplest atoms you can imagine. And there are two types of forces between such atoms. First, there are London dispersion forces. They act at longer separations and they are always attractive. These forces are usually explained by the fluctuating dipole model. The reason is the following. Let's have here such an atom, and it is composed of a nucleus, which has a large mass, as you know, and electrons. These electrons are in motion. Even if we use quantum mechanics to describe them, these electrons are in motion. The question is why. You are perhaps used to show molecules just as such balls, or perhaps you describe orbitals. But if you apply an operator of kinetic energy to such orbitals, you will get something non-zero. That is, electrons are in motion. And they are essentially in random motion. It means that once a while there is a dipole moment created, instantaneous dipole moment, that by chance most electrons or some surplus of electrons is on one side with respect to the nucleus and another at the other side. It means that there's an electric field, a dipole electric field, which is expressed here using the force lines. If I have another atom here, it interacts with this electric field. Essentially, it is polarized. That is, a tiny dipole moment is created which reflects this electric field at this point. The magnitude of the electrostatic field at certain distance r from this atom is proportional to the inverse third cube of the distance. It also depends on angles, but it's not important for now. The induced dipole is proportional to this electric field. This is the induced dipole at this atom. And the energy is proportional to the product of the dipole moment, that is the induced dipole moment now, and the electric field, and it gives the term 1 over the distance to the 6th power. And these forces are attractive. According to the Lattice principle, this polarization acts against this, and energy has a tendency to decrease spontaneously. That is, these forces are attractive. At very short separations, atoms repel each other. That's because essentially the Pauli exclusion principle. We cannot have two orbitals very close together. The electrons would overlap. Quantum chemistry gives very roughly such a general term for this repulsion. It's an exponential. So we can smash atoms close together, but we need a lot of energy. If we put two nuclei very close together, a chemical reaction occurs. So that is another process. It will not be covered here. To summarize, we have two types of forces: the attractive forces and the repulsive forces. And we can merge this to one formula, which in the simplest case looks like this. Here A, B, and C are positive constant. So it is because of this repulsion that decreases with distance. B is positive, we have minus here, A is positive because we have repulsion, and here we have a negative force. Such a type of potential is quite useful. It's called by several names. There are several flavors of it, either Buckingham potential or Born-Meyer potential or Tosi-Fume potential, or simply Exp6 potential. And such a potential is a component of any atom-atom interaction. We have other types of forces between atoms. Of course, I'll cover these forces later. From the computational point of view, the exponential function is more demanding to calculate, or at least it used to be. So Mr. Lennard-Jones discovered one simple way how to simplify this. He replaced this exponential repulsion by simply another term, which is a square of this attractive term, in fact. So we need only one multiplication to calculate it. So the computer code and calculations are then easier to handle. That is, we have two terms, a repulsive one, this one, an attractive one, and it's quite common to rearrange the constants in such a way which is written here. Here we have two types of constants. Sigma corresponds to the size of the atom. Actually, sigma is the distance at which there is zero energy between these two atoms, and epsilon is the magnitude of this attractive well. Why is 4 here? Well, you can try it by yourself. What you need to do is to calculate the distance of the minimum potential. That is to take a derivative of this. This derivative then equals 0 at the minimum. From this we calculate the distance, and we'll find that the minimum distance is the 6th root of 2 times this sigma. And by back substitution we'll find that the minimum of this potential is minus epsilon, and that's why we have the number 4. It is possible to express the same principle by another formula, but this one is much more common. So this type of potential, like Lennard-Jones or X6, is the main part of any atom-atom interaction in any force field. So let's have liquid argon. It's a simple liquid. All molecules are spherically symmetric, so it's easy to calculate. We like it because argon is still hard enough. Xenon is very soft, a lot of three-body forces and so on. Helium is quantum, so argon is, from the theoretical point of view, the easiest liquid to describe. And we know that we have interactions atom-atom, like here. So the key idea is, if we have many atoms here, to take all pairs and simply to sum up all possible pairs. I wrote it in a simple way like this. The sum means that the sum is over all pairs of atoms. If we have n atoms, the number of such pairs is n over 2, a binomial number. Okay, so we can be happy with this and say, well, this is our approximation of the energy, but this is not the full truth. Unfortunately, because of the same reason as explained before, that is, the London dispersion forces are or originate from fluctuating dipoles and a response of this fluctuating dipole with other molecules. We have also a three-body force between these. It is polarized in some way, but the third molecule or the fourth molecule interacts with these two when these two are interacting. That is, this approximation, so-called the pair additivity approximation, isn't exact. In general, we should add a third term which would consider sums over all triplets and so on. And this three-body potential is defined from, I will draw it again, in general from such a triplet of atoms in such a way that we'll take the total energy of these three atoms and deduct all pair contributions. Very approximately such a rule of thumb, such three-body forces are about 10% of the whole interaction. It means that this pair additivity approximation is qualitatively okay, but quantitatively it is not so exact. But still it is simple, and it is the most common way how to construct force fields. Of course, we can hide these many-body forces in certain effective terms so that the total result is accurate. In addition to these repulsive and attractive forces, we have electrostatic forces. For example, charge, which appear if we have an ionic system, let us say molten salt and so on, but also if we model complex molecules, we put partial charges to individual atoms and treat them by the same formula that I am sure you know from physics. It is not quite easy to assign partial charges to individual atoms. The task is complex. Instead of point charges, we have a complex electronic cloud around. And we must, for a molecule, for example, maybe a molecule like this, you can imagine water. So we can, or we must, elaborate such charges so that they best mimic the electric field of such a molecule. There are methods of quantum chemistry how to do this, but it is not an easy task. We can also consider in the construction of force fields a dipole moment, you know from physics its definition, and also other types of forces which are not pair additive, like polarizability. It means that under an electric field, a dipole moment is induced. I've already spoke about this. So if we have electric field, the electric cloud distorts, and this is the source of the induced dipole moment. That is, polarizability is not pairwise additive. Normal electrostatic forces are pairwise additive. Now we have a lot of terms, and if we put them together, we describe the potential energy surface as a sum of contributions. There may be very many such contributions. They may have many functional forms. We can have rich tables of parameters. If we have small molecules, these molecules can be considered as rigid. For example, for water, this is pretty enough. It can be shown that a molecule of water at the boiling point has less than 1% of molecules in an excited vibrational state, so that a rigid approximation isn't so bad. But of course, there are rotations of these molecules. So this rigid molecular approximation is good for the smallest molecules. If we have large molecules like peptides, proteins, nucleic acids, and so on, we have many terms. And we must also describe the so-called bonded forces. That is, vibrating bonds, angles, torsions, and dihedral potentials. Here in the scheme, these numbers correspond to the number of bonds between, that these angles comprise such triplets, torsions comprise 4 atoms bonded in such a way. So these are the so-called bonded forces, and the rest are non-bonded forces. That is, non-bonded forces are these Lennard-Jones forces, charge-charge interactions, that is, Coulomb forces, and essentially that's it. But there is something that is solved differently in different force fields, that is how one interacts with 4, that is, if we have 3 bonds in between. This is such an intermediate case. We model this usually by torsion terms and non-bonded terms, that is charge-charge and Lennard-Jones, between 1 and 4. That is, we use both types. But that 1 and 4 is usually scaled down or fitted independently. Typically, that 1, 4 may be about 1/2 of the interaction of the same types of atoms which are farther away. As regards the types of atomistic models, we have full atom models, that is, all hydrogens are included. We can have simplified models where such groups which are not very dipolar, like methyl or methylene, are treated as one Lennard-Jones superatom, or called united atom, which is larger. But we can also work in the opposite direction. For some models, especially for water, it's important. We move the charge from oxygen somewhere off oxygen to the center of the molecule, and we'll get a better model. These are auxiliary interaction centers. Of course, we can continue with this coarse graining up to true coarse-grained models. I will show you now one small peptide in the force field, which is called charm 22. It's quite older. Carbons are the cyan or light blue, sulfur is yellow, oxygens are red, and hydrogens are white, and the nitrogens are blue. It's quite typical. I can, in this software, let us run energy minimization and so on. This is the same molecule shown using a ball model. And this is the same peptide, however, in a simplified united atom model. If I show atom times here, I have here a methyl as one ball, one atom. It is quite cheaper to use this model, but it is also less precise. In this type, I can also show partial charges which are assigned to different atoms and other things. And it is the same model using balls. So this is methyl, this is methionine, sulfur, and this is just methyl without hydrogens. Bonded forces are quite important, and the most often used approximation is just a harmonic approximation, harmonic potential. I guess you know about the harmonic potential from physics. It's just square of the distance from the equilibrium distance times certain constant. There are two options how to write this constant in this or that way, but it's not important. This is one approximation which is possible. If we need dissociation, we'll use the Morse potential. Also, often this is too complicated, especially for bonds that contain hydrogens. Hydrogens are fast. That is, another approximation is just to use a fixed bond length. At the simplest level, this is the case of water potential. Usually water models or many water models used, let us say, in biochemistry are rigid, so that not only the bond length is rigid but also the angle. But usually angles are not angles are kept as rigid only for very simple molecules. The second type of term in a force field are angles. Again, the most common way is to use a harmonic potential. There are other options, but not so important. That is, we have set an equilibrium potential, and this molecule can vibrate in such a way. Another term, a more complicated term, is a so-called dihedral potential, or so-called proper torsion. It is usually written as a sum of cosines, that is, Fourier series of such a potential, which is of course periodic, and the angle phi is the angle between two planes. One which goes through 1, 2, 3, that is, it is around bond 2, 3, and the other is 2, 3, 4. And the angle between these two planes is called the dihedral angle or torsion angle. Usually this is combined, as I've already said, with non-bonded forces between 1 and 4, and it must be adjusted, fitted to the properties of molecules together. Also, sometimes it's useful to keep some terms planar. Let us say, if this is carbonyl, for example, this term, we use a term like this, or perhaps like this, the same type of formula to keep this in one plane, aromatic rings and so on. Okay, so let's proceed with non-bonded forces. In the simplest case, these are the Lennard-Jones terms. We already know what is the potential between two atoms. But what if we don't have argon, but we have many types of atoms? Then we have many terms. We can adjust these terms between the like atom, that is carbon, hydrogen, and so on. This is then given by this formula. But if we have n types of atoms, we have many pairs. So it's a good idea to be able to calculate the cross term, that is the interaction between unlike atoms, from the parameters of the pure atoms, of the like atoms. This is accomplished by the so-called combining rules. Of course, there are many combining rules, but the most common two are the following. Usually, for the energetic terms, we use the geometric mean. For atom sizes, it is natural to use such an arithmetic mean. It means that if I have one atom here and another atom here, and they are approximately in touch or at the minimum distance, this minimum distance is the average of both terms, or radius of one atom plus the radius of the other atom, radius the half of the diameter sigma, and so on. It is often used. It works quite fine, for example, for vapor-liquid equilibria. But it is known that in crystals this is not so accurate. Then we use the geometric mean here too. Or if we wish to be very precise, we must adjust these cross terms and have rich tables of all these terms. This is then called sometimes non-bounded fixes. That is something that fixes the combining rules. Okay, we know now that we have a force field. It is a set of formulas and we need parameters. And the question is how we get these parameters for a force field. That is, what is the force field development? So what we need? First, we need the geometry of molecules. That is bond lengths, bond angles, and so on. For small molecules, we can get it from spectroscopy, from rotational spectroscopy, from vibrational spectroscopy, and so on. Also, for solids, we get the structure by diffraction. Diffractions are of different types. Usually we use X-ray, it is the cheapest. We can use also neutrons and electrons. All quite well. The quantum chemistry calculations work here for bond length, bond angles, and so on. Also, we need the bonded forces. Sometimes we can replace bond vibrations by a rigid model, so then we don't need it. But generally here we can use quantum chemistry calculations, often with certain, if we have a more complex molecule, it is known that typically quantum chemistry calculations gives higher frequencies by, let us say, 5%. So there are certain empirical parameters how to get a better value, or from spectroscopy, vibrational spectroscopy, Raman spectroscopy, and so on. As regards the Lennard-Jones sigmas, here we usually start with experimental density or densities of many substances and mixtures, or from a structure of a crystal, for example, obtained by diffraction. As regards the Lennard-Jones epsilon, this is the energetic parameter. Sigma means the size of the molecule, that is, density is appropriate. Here we use usually the vaporization enthalpy. This vaporization enthalpy is related to the mean potential. That is, we have a force field, we can calculate the potential during a simulation, and the average potential is the vaporization internal energy. But in the tables usually have vaporization enthalpies, so we must convert this using your well-known relation between the internal energy and enthalpy for ideal gas, usually. Perhaps I should write the formula. What you know is that enthalpy is internal energy plus PV. If we have a liquid and a vapor, usually we can neglect the volume of liquid and use only vapor, and that PV get from the ideal gas equation of states. That's why we got this formula, which is not exact, it's approximate. If we use the X6 potential, or we can adjust better Lennard-Jones, we can treat repulsions more precisely by compressibility or modeling crystals using elastic moduli. What is very important, especially in simulations of biological systems, are partial charges. We can get them for small molecules from spectroscopy, and from the properties of liquid, from the permittivity or the dielectric constant, or from quantum chemistry calculations. In the quantum chemistry calculations, we have several types of point charges estimated. Usually the Mulliken charges aren't so good, and the method of first choice are grid-based methods. These grid-based methods start with a molecule which is calculated quantum mechanically, and they put this molecule into a grid and calculate from the no orbitals electric field outside these molecules or the electric potential at these grid points. And then they fit the partial charges at atomic nuclei in such a way that this best describes the observed electric field in the grid. Typically, if you start a calculation with a force field, you may have problems with partial charges. They may be inaccurate or not available at all, but usually you have Lennard-Jones parameters and geometry and so on. So you'll use these parameters, but you'll take a quantum chemistry software like Gaussian or something like that, Orca, MoPro and so on, and calculate these partial charges for these molecules from quantum chemistry calculations. You can also use pairs of molecules, for example, for ions, because ions usually interact a lot, so free molecule isn't enough. In the process of development of force fields, we use also clusters which are calculated by quantum chemistry. That is, we observe the geometry of clusters, their interaction energy, perhaps vibrational frequencies, and so on. For example, for a water dimer. Polarizability, it is a type of more sophisticated force field, are taken either from experiment or from quantum chemistry calculations. Fine-tuning of several terms or their relations can be obtained by diffusivity. It is important, for example, for water, because we have both partial charges in a water molecule that describes hydrogen bonds, and then we have these two terms and they are in certain relation, and it's difficult to fit them together, and we need another property to fit, and this is diffusivity, because it tells me how fast are water molecules in water, and it's important for a realistic description. And last but not the least, we observe the structure. The radial distribution functions the structure of liquid, and there are even methods how to get the force field directly from this structure description. These were forces, let us say internal forces, that is between molecules. But often we study our systems at hard walls, at certain external forces and so on, or in pores. It is quite popular to study zeolite. They are such porous materials. It is just one type. There are many types of zeolites. They have cavities where different molecules can be absorbed and can serve as catalyst for many types of reactions. So we can make something like this from atoms. We have an atomistic model. It's simpler to have a hard wall. Hard wall is a hard wall, so the potential depends on one coordinate. Let us say it's the z coordinate, and either it's infinity, that is, we cannot have a molecule there, or it's zero. It is also possible to have a wall composed of different types of atoms. So we can imagine a crystal, but instead of calculating explicitly for each atom in this crystal, we'll smooth this out. That is, we integrate. In this case, the interaction of an atom which is somewhere here outside this wall. That is, we are looking, let us say this is the z coordinate. So we'll integrate over this half space. We need 3 interactions, 3 integrations here. 2 are from -infinity to +infinity. These are x and y, and the third one is only from 0 to infinity, and we'll get such a potential. It looks like here it would be better to write z instead of r in this case, because it depends only on the distance, so it is the same. I'm not going to derive this formula, it's not necessary, but I will give you one homework where you will use this formula to calculate the force of an atom from a wall.